KD8OXT, covering the WWV 100 results and Festival of Frequencies. Kristina has an MS.EE working with robotics and space-based optical communications and is currently a PhD candidate in electrical engineering. Kristina has promoted amateur radio as an educational tool at the college level and has other ham radio interests, including DXing, collecting QSL cards. Kristina, take it away.
There's the unmute button. Well, thank you very much for that, Bob. That's, my God, that's going to be a tough act to follow. Oh, whoops, hang on. My, let's see. Excuse me a moment, I need to turn narration off in my PowerPoint. That got turned on somehow. I apologize for that. Sorry about this, folks. I'll be right with you in just a moment. I didn't have this problem when I was practicing it for some reason. All right. All right, I'm going to try this once more and hopefully I don't end up talking over my own narrations. Maybe I will. Okay. Okay, that'll do. So, thank you very much for having me. I'll be talking today about the Festival of Frequency Measurement, which we held during the WWV Centennial in 2019, and some of the projects that we're working on for an initiative called the Personal Space Weather Station under the auspices of HAMSci. So first, a word from our sponsors. The Case Amateur Radio Club here at Case Western Reserve University in Cleveland, Whiskey 8 Echo Delta Uniform, home of the Rock and Roll Hall of Fame. Come and visit us. Here's a image from when we held the HAMSci conference here back in 2019. You may recognize some equipment. HAMSci is the Ham Radio Science Citizen Investigation. It is a collective of amateur radio operators and scientists who work on bringing the best of the two worlds together. and using amateur radio tools to do science and bringing scientific findings to amateur radio to give people a better understanding of things like maximum usable frequency at their QTH in order to get better at doing DXing and so forth. Now, fortunately, Rob already covered some things about why we all care about space weather. Most of what I look at is the day-to-day variation in the ionosphere at mid-latitudes, and that's going to be the theme of the upcoming HAMSCI workshop, which we'll be holding in March. Will be mid-latitude ionospheric physics, since there are so many ham radio operators in that region. The Personal Space Weather Station is the project that we're working on right now. And there are a couple of different forms of this, and I'll be talking about the low-cost version, which is the standard station receiver, and it focuses specifically on picking up signals from WWV and other time standard stations. But in general, the Personal Space Weather Station is exactly what it says on the tin. It's a central computer where you can plug in several experiments, and we can build a network of hobbyists who are taking measurements that can be useful for geospace scientists in figuring out information about the ionosphere and its coupling into other parts of the geospace system. So by building better bases of information, we can start to draw correlations between forcing of the ionosphere from the terrestrial weather systems below and from the space weather systems above. So it will be an SDR as the most central component, the bigger model, as it were, what we're calling the Tangerine, is being built by the hams at the Tucson Amateur Packet Radio Network, and then the initiative that we're focusing on at CASE is the small station, which we're calling the Grape. Since we're talking about stations in Colorado, really what I'll be focusing on here is the notion of WWV and other time standard stations as a scientific utility, as a fountain from which data flows. We are using them as a passive radar beacon. And as the heartbeat of the electromagnetic spectrum, there's a really wonderful element to being able to draw scientific data from this thing that is one of the first things that so many people first encounter when they begin shortwave listening. So before I get into it more, I do want to take a moment to address my title, The Lion in the Path, because I think that this is something you'll enjoy. This is my standard title for this talk, and for many talks otherwise. I picked this up from someone who got it from his advisor. This has been traced back to Professor Howard Comfort at Haverford College, who gave the advice to his students that at some point in your career, when you're asked to give a talk at a conference, you'll know that you want to go, you'll know that you want to give a talk, but you won't really know what you want to talk about. He said you should call your talk The Lion in the Path when you're asked to give a title, because it sounds very impressive and it means absolutely nothing. So you can talk about whatever you want when the time comes. So I used this a couple of years ago when I gave a talk at the Tapper Digital Communications Conference on the early phases of this project. And I took a liking to it because if you think about it, we have our beacon in the form of WWV and we have our receiving station. And in between, we do have a path. We have a propagation path. And we are in the business of trying to identify the lions and the tigers and bears and other wildlife, which are inhabiting this propagation path. The different short and long-term variations that we see in the ionosphere. Because the wonderful thing about this and why this is such a fun moment to be at is that the ionosphere is a deeply undersampled system. So I want to make clear, there's nothing new about doing Doppler shift measurements in order to gauge ionospheric height. I've got a stack of books here from the 50s and 60s, and they have figures in them from the 20s that are essentially doing the same basic sorts of measurements that we do now. What's different about the way that we're doing them is that we have single board computers, so we can put these things everywhere. We have inexpensive, comparatively speaking, inexpensive, higher degrees of precision available in the form of really good GPS disciplined oscillators. and we have the amateur radio community. And hams are naturally disposed toward citizen science, and particularly citizen science regarding space weather, because we've all built up an intuition for it. We all know what it's like to try to reach that contact in the Azores right as the sun is going down. And you get a feel for when those propagation paths are opening and closing, because you want to know when you can talk to people and when you can rack up contacts and when you cannot. So you're already doing a little bit of empirical space weather analysis on your own all the time when you're operating. So a very basic walkthrough of how Doppler shift measurement works. And this is quite simplified, and I'll get into some of the parts where it's not adequate in a minute. But this is one of those things where all models are wrong, but some are useful. So if we imagine this, this layer of things that we're bouncing our radio waves off of as being a surface, and it's moving up and down, right? Here we have on the left, WWV, we have our beacon. On the right, we have our receiving station here in Cleveland. And in the middle of that fixed path, you have a point that's, roughly 90 miles outside of Des Moines, Iowa. So if we make a few assumptions about that midpoint not moving, then my station in Cleveland, when listening to WWV, can give me information about what the ionosphere is doing at that point. And when the ionosphere goes up, the path that is taken by that radio wave to reach me increases in length. So it becomes redshifted. So that 10.00000, et cetera, it's 1 in 10 to the 12th, I want to say. So I will, 1 in 10 to the 12th. Precision signal from WWV drops a little bit because of that that increased path length. Those wave fronts get stretched. Conversely, when the virtual height of the ionosphere drops during the day, the path length decreases, the wave fronts get scrunched together, and that received frequency goes up just a little bit. So I can get information from just setting up my radio to listen to the carrier frequency of WWV and measuring how that frequency changes. And this variation happens every day. It's got sort of a tidal quality where you have a jump around sunrise. Sorry, there's pesky narrations again. Okay. So if you do this every day, right, we've got a couple of charts here which were taken by David AD8Y, and you can see this this peak in the middle on the top. That's his WWV 5 megahertz observations from, looks like, March through May of 2020. And that peak is right around local sunrise. So you can see it moving backwards as local sunrise gets earlier. And I need to take the rest of the data set from this year and put it into that so that we can see that go all the way back and forth. But there's also all of these little bits of variation that you're seeing, and those are related to waves that travel through the ionosphere, to traveling ionospheric disturbances. So this is a measurement technique that you can set up in your own ham shack, and in fact, it's quite easy to with FLDigi. And we're exploring having many ham radio operators do this at once. So I'm going to assume that everyone is familiar with WWV, with the fundamentals of its broadcast format, with the familiar at the tone, the time will be, and with WWVH, the sister station in Hawaii, that as far as the carrier is concerned, is singing the same tune at the same time, but has a slightly different modulation schedule. And there's a lot of different approaches that we could use for measuring this. We could look at the second ticks themselves. We can look at the A440 tone that is played every hour, except for apparently when the Heights Orchestra meets, which is how we know it's not played at 7 o'clock. I don't know. I think there's 1 hour that they skip, and that was like the one time that I actually knew somebody who tried to use that for an A440 standard. You can listen for the audio sideband, and there are digital codes that are on there as well. So these offer different pros and cons for how you might make these measurements. But the one that we're focusing on for this particular experiment is just that carrier, just that moving up and down thing that was in the previous slide. If you're looking to buy a GPS-DO, by the way, I highly recommend the Leo Bodnar. This has been our go-to. And apart from the fact that it doesn't have a 1 PPS signal broken out on a pin, it's very easy to use, very easy to control with a computer, and very good resolution, very, relatively inexpensive, straightforward for these sorts of applications. So this has been the one that we've been recommending to everyone as a GPS-DO for their station. So the standard station receiver, again, in the Personal Space Weather Station initiative, this is specifically a radio receiver that is built just to receive WWV. It's receiving it on all available frequencies, then also receiving the Canadian Standard Station CHU. So it's got several channels for this. And these are, measurable frequency shifts for an ordinary radio set, but you'll have a much better time if you have a GPS-DO. So if you have, let me move my Zoom box out of the way here. This is a diagram for what one channel of this looks like. You have your antenna receiving WWV, and then you are comparing that to the GPS-DO. You set your radio to be 1 kilohertz below the carrier frequency so that you pull out that 1 kilohertz audio. Now I am narrating over myself. Can I get rid of that? I don't know. I will jump to the next slide and then start from there. Thank you for your patience. Or perhaps I'll just do it in the non-slideshow mode for now. That's probably the 80-20 solution. All right. We will embiggen that and ensmallen that. Hopefully that's relatively visible. So this is what the prototype station looks like. And we've been calling this the grape in lieu of the tangerine. And this was one of our first generation prototypes. The first generation only does 1 channel, but we've set up a few of them as pilot stations. And the second generation will hopefully be done within the next year. I'm aiming for the summer because there's a couple of events that I'd like to deploy it for in particular, but we'll see. That will have a little bit different means of measuring frequency, and we'll have multiple channels so that we can listen to several different standard stations at once. The reasons for calling it the grape: first, because it is easier to say than its proposal name, which is Low Cost Personal Space Weather Station. Also because it is a tiny fruit and people like to name electronics after tiny fruit. I am screen sharing properly, yes? Yes, okay. For instance, you have the Kiwi SDR, the Lime SDR, obviously the Raspberry Pi. It's like a whole thing. And then the other explanation we like to say is that it does its best work in bunches, and we hope that the data will ferment into something quite nice. So you don't need a grape in order to start taking these measurements, and this is one of the things that we have going. So if you have a spare ham rig and you'd like to explore some of the ionospheric elements in your region, you can set that up in a fairly straightforward manner by using FLDigi. There's a mode in FLDigi called frequency analysis mode that is optimized for this purpose, essentially. Its real purpose is for the ARRL frequency measuring test. And I don't know if folks here are particularly into the frequency measuring test, but its general form is that there is one ham radio operator who is known as the Connie, named for the first person to take on this role, who has a NIST traceable frequency standard. And they transmit on a frequency that's in a given range. They key down for some period of time. You know, so between say 9 o'clock and 9:05, right? There will be a signal that is around, but not exactly on 7.2 megahertz, for example. And everybody tunes their radios to that, finds that line on the spectrum, on the waterfall plot, and does their best using whatever techniques are available to them to work out what that transmitter frequency is. The up and down motion of the ionosphere that I showed earlier is noise, if that's what you're trying to do. It gets in your way. It's an additional component that is likely to screw up your estimations. But if that's the number that you care about, we can use the same basic function to rely on WWV's precise carrier, and then particularly if you have a precise frequency standard at your home station, we can use that that precision to pull out that component and gather information in that way. So something that is a disadvantage in the original use case becomes very central to what we're able to do. And because it's already integrated into a pretty common amateur radio program, it's an easy enough thing for hams to do when operating. So WWV, of course, turned 100 a couple of years ago, and after a bit of a dicey process, was able to survive the budget cuts that were proposed under the NIST. And part of that was the recognition of it as not only just a really cool thing to have in general, but also that it has this potential for scientific purpose. So there was the wonderful WWV 100 celebration. We had a delegation from CASE go out there, and we spent a week operating WW0 WWV, which was the special event station for the occasion. And this was the certificate of participation that I prepared for the Festival of Frequency Measurement. So while WWV 100 was going on, we also put together this event where we asked ham radio operators to set up their station in a particular way and collect frequency information from the WWV carrier. We got 45 stations who recorded data on 5 megahertz. Many did have GPSDOs. There's a couple of stations. There's one in Australia that doesn't appear on this map, and there are some stations that recorded on other carrier frequencies during that time as well. But our analysis for this particular thing has been confined to the 5 megahertz data. And here's one where, let's see. Typically, I have animations for this, but I will get rid of them for now. So the metaphor that I like to use here, returning once again to the wildlife metaphor. There's this poem by John Godfrey Sachs, The Blind Men and the Elephant, which I'm very fond of. And it's usually used to describe religious debates. But the premise of it is that there are these blind men who come across an elephant, and the mural here is on one of the walls in the corridor at MIT. And I'm fairly certain is meant to be a reference to the poem. I'm not sure what else could be going on. And so the blind men come upon the elephant, and they each analyze that part which is closest to them. One comes up to the elephant's leg and goes, oh, this is shaped like a tree. That must be what an elephant is. An elephant is tree-like. Another one finds the ear and proclaims it to be a fan, and so forth. And they have this big debate about it. And I found that I was having this debate with Steve Serwin, WA5 FRF, about what WWV was like at night versus during the day. Because to him, in Texas, the signal of WWV, that carrier, is very clear during the day and not clear at night. For me in Cleveland, it's the opposite. So we had years of lived experience of listening to this signal, and we were experiencing a different thing because we had different ionospheric conditions. His ionosphere is not the same as my ionosphere. And in fact, my ionosphere isn't the same as the ionosphere is for my friend who lives down the street. It's just not quite as different as mine is from Steve's. All right. So I'll take a moment to walk here through how we organize this data. This was what we had submitted. And each of these plots, it's a bit of an eye chart. Each of these plots is one of the stations that submitted data for the Festival of Frequency measurement. So these are sorted by longitude. And we're going, the way that this is laid out, it looks like it's going west to east. And you can see when you look at them that there are certain sets that kind of agree with the stations that are near them. And then there are others that, you know, clearly this one has an instrumentation error, this station turned on and off, there's something that's washing this out, etc. But the ones that agree with each other don't necessarily see very similar trends to the ones that are on the other side of the country. So then the next thing that we do is we add some filtering and we wipe out those signals which are definitely indicative of instrumentation errors. And once we clear those out, we've moved them here to the end of the plot. You begin to see that these regional perspectives become much clearer. That stations that are in the same regions are showing similar patterns. This is for one UTC day. We did October 1st from midnight UTC to midnight UTC. Now you'll see vertical lines on these plots, and those correspond to the sunrise and sunset. Sunrise is the dotted line and sunset is the solid for those stations' particular locations. And there's always that bump right around sunrise as you see the, there's usually, I think, a drop for the formation of the D layer. Here's a zoomed in version, and this has been submitted and accepted. It's in the revision process now for IEEE Geoscience and Remote Sensing letters. So we'll be reporting on these results. All right, so now I'm gonna try to show you these animated slides and make sure that I ditch the narration for them specifically. Because I didn't precisely, let's see. Can we do start from current slide? PowerPoint, why have you betrayed me? There we go. Does that work? Maybe not. Ah, there we go. Perfect. Okay. So when I showed you the figure earlier, it implied that the midpoint, that for Cleveland, the midpoint is Des Moines, Iowa. It implied that that midpoint was fixed. And I do like to think of scattering these stations around the country as each station is sort of filling in a pixel in a display. But it's a little bit more complicated than that, and it deserves to be addressed in order to make sure that you know, we don't get into this misconception that that is a static point. And also because it's rather interesting in terms of your bearing relative to WWV if you choose to make these measurements at your own station. So these are simulations for Cleveland on 2.5, 5, and 10 megahertz using the International Reference Ionosphere model, which is the ISO standard reference ionosphere. And it is based on monthly averages. So this is kind of it gives you a bit of a cartoon drawing version of what's happening. All of that local variation that we saw in the plots that we took, you're not going to see that here. What you will get is a general sense of what the rays are doing between WWV and your station on an average day in a given time of the year. And you can model seasonal variation and see some things like that. These were generated in MATLAB using the FARLAP toolkit. So again, 2.5, 5, and 10, you can ignore the color maps for these. They, the actual ionospheric information is the same. So that's the Cleveland view. Here's what Steve is seeing at his station. So there are lines on these plots. This is his 5 megahertz plot, so it should be compared to the middle plot for Cleveland that's in the previous image. And I want you to take a look at where the apogee of that ray is, the highest point, versus the halfway point in terms of latitude and longitude. You'll notice that from Colorado to Texas, the halfway mark is pretty constant, whereas it jumps by, you know, hundreds of kilometers in the 5 megahertz trace for Cleveland above. So you have to account for the fact that there are multiple inputs, and the best way to begin to address that is to collect data from more stations and find stations that are appropriately located so that we can generate experiments for those particular phenomena. For the Festival of Frequency measurement, we just put out an open call and had people submit data according to those procedures. And I think we did very well under those circumstances. But as we're progressing forward and developing more things for the personal space weather station, that's one of the things that we'll be looking at, is how to appropriately locate stations to test for certain things and to come up with approaches to putting together the data from multiple points. So again, here's what this simulation looks like when we account for that changing apogee. I'm using a color scheme here where there's pink is the F2 layer, and then the dark purple is the E layer, and then that sort of middle purple is the F1 layer. And this is over the course of one day. This is in simulation. There's no data here. But each of the yellow dots represents a station reporting data for the Festival of Frequency measurement. And this is the simulation of whether a ray from WWV at a normal elevation angle will hit that station, which layer of the ionosphere it will bounce off of, and where it will bounce off of that layer. Here's what happens when we break it out by layer. So we have layer E, F1, and F2. And you should see the terminator come across. There you go. The timing is in UTC, so time shift as you will. So you'll see that here we are during the day. So there's some layer E propagation that doesn't make it all the way to the East Coast. And then at night we have that layer F2 propagation. So the ionospheric ceiling has risen, and we're able to get signals out at stations that are further away. So the next thing we're working on is we're taking those little grape prototypes, and we're setting up stations along this great circle path that goes through WWV over to our location in Cleveland, over to University of Scranton and the New Jersey Institute of Technology, which are other heavily represented HAMSci locations. Dr. Frisell, who is the main founder coordinator for HAMSci, is at Scranton. And then other participants in Personal Space Weather Station are at New Jersey Institute of Technology as well. We have a station at Cal Poly that's going to be starting up later this year, and we have an extremely enthusiastic high schooler in Fort Collins, whom I just got our first round of data sets from, who's taking the ground wave data, as it were, from the area right around WWV. So we'll have a point of comparison. And then when we do those ray traces, it will all be along the same bearing from WWV. So that's our current long-term project. Back to the narration problems. Okay, so there we go. So the Festival of Frequency Measurement was the first in several pilot experiments. As we're putting together this network of stations, it's best to undertake it as an iterative process. The paradigm of coming up with the notion of how we would lay out a network and how we would determine the needs for instrumentation. And then once we figured that out, we would design it, we would provide it to ham radio operators, make it available for sale, send stations to people, etc. If we only go through that once, we never get a chance to come back to the earlier parts and rectify our mistakes. We never get to realize that actually our bandwidth was wrong, or that we needed to locate stations in a particular way, and on and on. So doing these pilot experiments as we're working on the development process for the system lets us skip over some of the harder questions and just focus on the data collection and the data analysis. It answers a lot of the questions that we would ordinarily have about where do our stations go, how many stations do we need, what are we looking for? And because we can reach out to people specifically using QRZ and things like that, we can get ham radio operators in certain regions. And we've been using that in some of the pilot experiments. So in some sense, one of the things that we're working towards in HAMSci and specifically at CASE is, as you probably know, there are going to be actually 2 eclipses coming across the United States in 2023 and one in 2024. We're excited for the 2024 one because we get to be in totality for that. Or as we've been saying, we paid handsomely to ensure that CASE would be in totality and MIT would not. And why is this important for looking at the ionosphere? Because solar forcing is such an important factor, and an eclipse gives us a chance to do something that approximates a controlled experiment in space. So you get to have a period where you know that there is no solar forcing over this particular swath, well, everything else is the same. And so setting up instrumentation for 2024 is a longer term project that a lot of different people are looking at on a lot of different bands, and there will be many experiments that are coming out of that. There's very good work done in 2017 by many of the folks at HAMSci, where they held the Eclipse QSO party, if you remember that one, where information from the reverse beacon network and Whisper and other existing ham networks, which are very easy to navigate if you're looking for data, because ham radio operators already wanted to make graphs of these things, so it's set up for it. Those were used to find traveling ionospheric disturbances resulting from the eclipse. So this is kind of our goal point, and we're hoping that we'll be able to get a full network of personal space weather stations across the country and take really interesting results from this when it happens. And of course, in 2023, there will be a different path of totality, and they cross over each other in a very nice way. So that'll give us a chance to prepare for the 2024 eclipse, which is a total one. but there's not really a reason to wait to do eclipse science, because there's a couple of eclipses every year. And this year there were two. There was one in June that went across Asia, and one just a few weeks ago that went across South America. So for the June one, I decided almost on a whim to set up another festival of frequency measurement and invite stations to participate for this. And we came up with, I think it was exactly 50 stations participated. I got all 6 continents. And the standard station we used for this was, I should note it on the map, BPM. That's the Chinese time standard station. So there's, in addition to WWV and WWVH, there's 3 time standard stations in South America, I believe, that are active. There's BPM in China, and then that's just the 10 megahertz set. There are other time standard stations on many different frequencies, and you can look at the BIPM has a report, and there's a pretty good Wikipedia page that summarizes them if you're curious about where these stations are and if you want to try picking them up. But we use BPM as the primary beacon for this. And I started out recruiting folks who were, you know, within that general region of totality. I put the page up translated into Chinese, and then I got a message from a Dutch ham radio operator at the ham radio group in the Netherlands, who's like, hey, I saw your announcement. Do you mind if I do an article about it? Do you need any Dutch operators? And I was like, I don't know. I don't know if you'll see anything interesting, but sure. So we opened this up to being a global event and people recording whatever time standard stations they picked up. And I was able to get some interesting results out of that. These were some of the articles that ran about it. We had the ARRL carried it. That was the original web page. Varen, Wireless Institute of Australia, and Southgate Amateur Radio Club were all very good places to recruit for this. And I didn't do any targeted recruiting for the June Eclipse experiment. This is the map of stations. I don't know why there's 2 copies of it, but here they are. You can see the path of totality there, and this is everyone who collected data. So there were several stations in the United States that collected for this. 1 guy in South America, so I was able to say that we got all the continents. And there were points that came out of this that I think will be very useful when we're thinking about how to structure our data collection networks. One notion that came out of it is the idea of grapes in bunches, as it were, of having several ham radio operators who are in the same almost immediate area running their receivers together. And there's a few reasons to do this. One reason is that it's more fun because you can compare the data that you have to the data that your friend down the road has. Another is that when you do this, you are sampling the ionosphere on a pretty small spatial scale, which can be scientifically interesting. And then another reason for doing it is that you have a way of checking parity when you have that. If my station is plugged into the power system in my house, and your station is plugged into the power system in your house, and your house is somewhat separated from mine, when there's a jump that we both see, I know that it's much more likely that it's geophysical in nature, as opposed to, say, my dishwasher turning on, or something causing RFI in my immediate environment. Here we have an example. This was sent to me by some of those Dutch stations, where there were 4 receivers, and the blue trace that you'll notice doesn't quite fit with the others is the one station that is not GPS disciplined. So another thing that that came out of this, and something that led to an interesting pivot when we were collecting data, was that the data I received from the stations in Europe all had this sort of fringe to it. And what I found was that there was a time station in Italy, not a recognized time standard station, but an experimental station that runs just underneath 10 megahertz. And the frequency estimation algorithm we were using in FLDigi got confused by this, because it was trying to sort of look for the loudest DFT bin. So it would just sort of jump from one to the other like a dog with two bones. And so I told everybody who was recording data, you know, with a week to go before the actual event, do you think you could record wave files of that? You know, instead of recording just like a tiny CSV file, do you think you could record an enormous wave file and send it to me? And again, a wonderful thing about the amateur community, people were very happy to go through that process. And we figured out ways of getting files submitted and testing all of that stuff. So that was a very useful thing when we came to the December eclipse. This one was a total eclipse. The June eclipse was annular. And this time there were 81 stations. And having looked at what we got for the June eclipse, the stations were asked to record just wave files, to record them for a full week instead of for just the 3 days we did for the June experiment. We did 1 day for the original Festival of Frequency measurement. And the reason for doing that is so that you get something approximating a baseline. And so I am still, you know, digging my way out from underneath an enormous pile of data at this point, which is on the whole a happy place to be. I have gigabytes from each of the 81 stations that submitted data. There's the map of them. And another thing that I found very useful for this particular campaign was when I went into QRZ. If you've ever used the QRZ list maker, you can pick a region and you can find amateur radio operators in that particular region. So I was able to take an evening and email every ham radio operator in the Falkland Islands, who were very nice about it, really. And I picked up a couple of people who were in really good positions that way, and have some data sets that I'm going through that were very well located. So there's more information on these and other experiments on the HamSci page, and there will be more data collection campaigns in the future. In particular, I want to draw everyone's attention to the upcoming HamSci workshop. This will be held in March, and we're currently collecting abstracts. Those are available on the submission is on the webpage, which is hamsci.org/hamsci2021. There will also be in this, and this is something that I want to put to the group for people to think about, what I'm calling a citizen science co-design session. So in citizen science, there is a spectrum of projects, from a project where the scientist needs some data collected to a project where the people who are working with the scientist, the participants, instead of just collecting data, instead of just analyzing something relatively passively, are actively involved in designing the experiment. And this is something that we're trying to develop more with HamSci. So something that we're hoping to put together going forward in this workshop, and if it's successful in others, are data collection campaigns that double as amateur radio contests, and not just presenting these for the consideration of the ham radio community, but actually having an active dialogue between the scientist who wants to collect data on a particular phenomenon and ham radio operators who are very adept at, say, contesting in the appropriate frequency band, figuring out what tools are available within the community for people to use for research. So if you have any ideas for that, please drop me a line. If you would like to submit an abstract, we have a very, it's a broad mandate. Anything with ham radio and science goes. Again, the main focus for this one will be mid-latitude ionospheric sensing, but we're open to things that relate to auroral propagation or amateur radio astronomy, or really anything else that that is of interest as either a talk or a paper or a poster. So definitely check out the HamSci website. And because this year's workshop is virtual, it will be free to attend. So please save the date, March 19th through 20th. And with that, thank you very much. And I'll take any questions you may have.
All right, there aren't any questions up yet, except I have one. And if anyone else would like to get a question into the Q&A portion of the Zoom function there, we'll relay it. If we run out of time, we'll use question@ncarc.net to get your questions answered. But Kristina, what's the size of one of the 1 week WAV file recordings?
Oh, let's see. Well, I can, I have to spin this up in my head again, because I used to have that on tap, and at the moment I don't. One moment. I actually have the files for all of them. I think you get about a couple of gigs a day, so multiply that out. And this is something where there's quite a few operators where I ask them to, we use box.com, which is much like Dropbox, but enterprise model, and our university supports that. So finding data storage for a project like this is really difficult when you're trying to do those big files. I think on average I got something like 10 gigs per, because people would have station outages, and of course, I don't want to tie up somebody's rig the entire week. If you want to run a net or something, please, turn it off, go do that, turn it back on, because this is part of the business of distributed sensing. You're going to have outages. And if your data processing can't handle that, then that's going to be a problem no matter what. So, this is meant to be something that people can set their radios up to do during downtime. Sort of like, SETI at home and the protein folding thing whose name escapes me, and other things where people have used excess computing power in a distributed way. This is kind of, you can think of it as an analog to that. I do have someplace here, I'm getting physical flash drives in the mail still with the December data. I just got one earlier this afternoon. So for people who don't have a reliable internet connection, it's easiest to just physically mail the thing a lot of the time. But yeah, uploading the large WAV files is certainly a lot harder than just the CSV, which is what you would call, a derived data product as opposed to raw data, right? But the reason for collecting the WAV files for a short-term experiment like this is that you're probably picking up many different stations, and you may want to look at information later that's contained in the sidebands and not just the carrier. So that was one of the reasons that I widened that. And I have a few different tacks that I'm taking in extracting that, but for the long-term stuff, the derived data product is generally sufficient, and FLDigi makes it really easy to collect. Okay, I saw a Q&A, somebody mentioned Eclipse mob, which I forgot to address, so thank you, Tom, for pointing that out. That was I want to say that they were in VLF bands. That's another project that was in 2017, and that was some of those results were presented at HamSci. They lost some data because of a software bug that hit them on the last day, which is really too bad because the rest of the project was amazing. There were incredible kits that they distributed to, as far as I can tell, every school in the country. Yeah. They had people, soldering and putting all of this together, and it was, just a really excellent effort on many levels. And we've talked a lot with folks from the Eclipse Mob team about how to take the lessons and the successes from that and incorporate them into future citizen science projects. Doing the kit-based stuff is effective, but I'm particularly interested in things that people can do with equipment that they already have. One equation that I have not worked out is if I were to actually add up, right, if I were to account all of the resources that were essentially donated to us during these citizen science experiments in the past year and a half, you know, there's something like, I don't know, 150 stations, because there's some overlap, right? There's like 150 stations in 45 countries who were donating time and power and essentially equipment. You know, it would cost me so much to try to duplicate that if I were to do it from scratch instead of asking the community to provide that data. And you know, I wouldn't have a highly qualified technician standing next to each one of these devices if I did that. So, and the other thing, I certainly wouldn't have been able to do it in a month, because the June Eclipse Festival was basically a 30-day thing. In December, I was recruiting people within, a couple of weeks of the experiment. So that was something where I think plugging into the existing community and the resources that are available there is a really great source of citizen science potential, and also is, another dimension for the hobby for people to be able to collect knowledge about what their QTH is in this additional dimension, and to have a deeper understanding and appreciation of the natural environment that we're all existing in, particularly as space weather gets more interesting over the next 11 years. See another Q&A. And the other thing that I will note for the December eclipse is that we did have that small geomagnetic storm that week. So I have one day where it was a relatively quiet ionosphere, and then the storm occurs, and then the eclipse. So that was one thing that changed. And another thing that changed was that the Argentinian time standard station, and I will leave you with this thought, the Argentinian time standard station's call sign is LOL. The Brazilian time standard station call sign is PPE. And LOL was turned on halfway through our data set by the Argentinian Navy as a way to provide a beacon for people who were doing experiments. I didn't specifically ask for it. I don't know who did, but I guess other people were also monitoring that. So I'm looking forward to having more of these global experiments, and also to having more targeted experiments that we can use to bridge between the ham community and the knowledge contained in the ham community and the scientific literature.
All right, well, we're getting pretty short of time. We're actually doing amazingly well given the entire day today. So it was an amazing data collection effort in modeling design. I want to thank you for the presentation, and good luck with your future endeavors.